Okay, so hello everyone. I hope you all are doing well and in good health in these conditions. So after a long summer break, we all are again organized here at our Young Senseco Talks. So today's presentation by Mr. Michal Antala, and he will talk about the influence of climate variables and vegetation composition and its phenology optical properties over the peatland vegetation. Indeed, Michal is my junior we both are from the same lab at Poznan University of Life Sciences. He's just started more than 1 year. He started his PhD, and currently he is working with Professor Radoslaw József and Dr. Ansu Rastogi at our same peatland vegetation site at Poland. So in his presentation, we will look after the different impacts of climate variables on vegetation compositions, particularly on the phenological perspectives through the optical spectroscopy of peatland vegetation. So the talk will be for 20 minutes, and after that, we'll start a Q&A session. So next 40 minutes would be the question and answer session from the audiences to Michal. So yeah, let's go. It's already 12:05. I think we'll start the presentation. Michal, are you ready? Can we start?
Yeah, so thank you, Subhajit, for introduction. I see I don't need to speak much about methods because you already said everything. So my name is Michal Antala, and as Subhajit said, I'm from Poznan University of Life Sciences, and I will speak about peatland vegetation and about climate manipulation and its impact on the vegetation and how we can sense it through remote sensing. I'm at the end of my first year of PhD, so this will be like what I've done in the 1 year, and is actually exactly 1 year from our last Senseco summer school. So I started with remote sensing in that time. So the first, what I want to tell you, why are we actually working with peatlands? Because for remote sensing, this is quite challenging environment. It would be much easier to work just with agricultural plants. And also the thing is that peatlands are just on the 3% of the terrestrial surface. If we think about it, there are 2/3 of oceans, that makes 1% of the surface of planet where the peatlands. So it looks quite insignificant. But if we start to think about the climate change and about the carbon, we will see that around 1/3 of all soil carbon on the planet is stored in the peatlands. This is because of the conditions in peatlands and the vegetation. It's water saturated environment. There is very low pH. There are just specific plants growing there. And all of the litter which is there, the dead plants, are falling basically to the water, and there's only very little decomposition. So this carbon is then stored in the form of peat. So now the peatland starts to be more significant. And why remote sensing? As I said, it's water saturated. There is low pH. Then people cannot even walk there because everything is floating. And the peatlands are around the boreal region. They are mostly in Siberia, they are in Scandinavia or north of Canada. So it's very difficult to get to there and monitor the vegetation, and remote sensing in this case looks pretty handy. Our experimental station is in Poland. It's in Szczecin peatland. It's around 200 hectares of peatland in the northwest of country, where we have currently 2 experimental sites. These experimental sites represent 2 different vegetation community. From now on, I will refer to them as CR and CL. They are marked based on the dominant graminoid species. Graminoids are kind of plants like grasses. So the CR is with Caryxostrata, CL is with Caryxolesiocarpa. Both of these sites contain 3 different climate regimes. First of them is control. Control is without any manipulation. There is only this frame in the peat, The frame is there mainly for carbon measurements or for carbon balance measurements by chambers, but it also marks the plots for us for remote sensing. The warming is induced by open top chambers, which are increasing the daily temperature by around 1 degree. And moreover to this, from this year, we have also infrared radiators, which you can see in the middle of plot for warming at night, because this is the passive warming. So before there was warming just during the daytime, now we have also nighttime. For our measurements, we can open these chambers. These are prototypes from our laboratory. It's possible to open the front door and also lift all of the chamber and completely open it, that there is just very little influence for our remote sensing measurements. The third condition is warming and precipitation. So warming is the same with the chambers and the radiators, and precipitation is cut only at the night time when this curtain is opening. And by this way, we can reduce the rainfall by around 20%. The results which I will present to you are from our Piccolo Doppio spectrometer. This is the dual field of view spectrometer. That means there are two for optics. So one is the upward for measuring of incoming radiance from the sun, and there is the downward, which is for reflected radiance. Both of these measurements are at the same time, so we don't need some wide calibration. The light from these optics, from these four optics, is going through fibers to two spectrometers, which are inside of the cooled suitcase. Inside of this suitcase, there are batteries. There is a control unit, and two spectrometers. One of them is flame, which measures from 400 to 1000 nanometers. This one is used for calculation of vegetation indices mostly. And the other one is QPro, which measures from 640 to 780 nanometers, and we use it for calculation of sun-induced fluorescence. And I will speak now a bit about sun-induced fluorescence and C field. So what you see on these graphs and on other three slides, the points represent one plot. In each plot, we measure 3 times and we do 3 reads from each point. So there are 9 reads from 3 different positions are represented as 1 point in these box plots. I will present only the far-red SIF or the SIF in O2A band at 760 nanometers. And you can see on the left graph, it's far-red SIF. In the right graph is SIF yield. There are 2 different vegetations. So upper is CL, down is CR, and the days of measurement which we measured. I want to show you 2 things in these graphs. First of them is why do we measure SIF, right? The SIF is directly connected to photosynthesis, and we can measure the stress of plants indirectly through the impact on the photosynthesis. If you look at the 16th of June, you can see in both vegetation, SIF yield was higher in manipulated sites than in control. This day was very sunny day, very warm day, and the vegetation you will see on NDVI was not that much different in these plots as there is the difference in sun-induced fluorescence. So I still need to do more analysis, but it looks like that we were able to measure the stress of the plants induced by climate change in June. The other thing which is interesting on these graphs is why it's better to speak about SIF yield and not SIF, especially if we are looking at a whole year when there is a change in light in every measurement. You can see in the CR, the last of the presented measurements in August, it looks like decline of SIF. But if we are looking at the sea field, it's still increasing. The reason behind this may be the light, because the SIF is dependent on photosynthetically active radiation and on the absorbed photosynthetically active radiation. So if we check what was the photosynthetically active radiations during the days, of course, at the beginning, we started in February, so there was very low bar. Then it was increasing till April, and it was quite stable. But as you can see, in August, it's already lower than it was before. And then we have our SIF, which is decreasing, but sea field, as I said, was still increasing. Other part of absorbed photosynthetically active radiation is fraction of this radiation which plants are using. So if we look at FAPAR, we can see the pattern at the beginning of the season when there is very low PAR, the plants are using as much light as possible. So even we can see that the highest use of light at the beginning. These plots are with mosses, which are photosynthetically active from very low temperatures. So they could even perform the photosynthesis in February. Then we can see a bit decline in fraction of absorbed PAR. And of course, with greening up, the fraction again increases. This decline is not because of plants would be less photosynthetically active, but it's simply because they may be still more and more, but not as much as PAR is increasing. Now, I will speak mostly about NDVI by the end of the presentation. So I'm sorry to everybody who thinks that NDVI is so simple index that we should move on from that, but it contains still a lot of information for us. You can see that there is one more measurement, also from September. I didn't include this measurement to SIF because it was quite cloudy day and the SIF measurements just didn't make much sense. But for reflectance-based indices, it was still okay, and I can still use it for analysis. One thing which I want to show you on this graph is NDVI and how much variable are our plots. So you see there is one leading plot and there was one lagging plot at the beginning. I will show you how the vegetation looked like at the beginning of the season, and you can really see that there are differences in vegetation and why there's the NDVI because of the greenness. So this orange plot is full of mosses and these shrubs with green leaves. This lagging plot is full of grasses, and actually the mosses somehow disappeared during the years of climate manipulation. But it's still the same community, there is the same hydrology, and all of the other plots are something in between of these two. If we now pay a bit more attention to this one plot, and you see that in May, there were no differences. This is the reason. There was the greening up, there was the growth of grasses, and by July, it was completely green. So the differences were mostly at the beginning of the season. If there hadn't been the summer school just a few days ago, that would have been the end of my analysis. But now I know about the data times, so I could perform some more things, some more analysis, and I wanted to model the NDVI for every day in between of our measurements, and then also the phenology. So first of all, I had to choose the right method. And you can see that all of the methods which are now on the slide are kind of ignoring some of the points. So I didn't like them much because I don't want to create the new measurement for my measured day. I just want to model the days in between. And that was exactly what Whitaker enabled me. So I was then just carrying on by Whitaker. And I modeled all of the days in between measurements. So the first day, which you can see, it's 25th of February. The last day on graph is 15th of September. That was the last measurement which I had. And the line in the graph represents the average of the three plots. And this shadow around, that's the standard deviation. So why I was speaking about these two plots in the graph before is also to explain this huge variation at the beginning for WP. That's caused by these lagging plots. And for warming, that was caused by this leading plot. But if you see the peak of the season, there was really little variation in manipulated plot, and in control, the variation between the plots was more or less stable during a whole year. Again, if we check our CR vegetation, the least variability was for warming and reduced precipitation around the peak. So far, this is just NDVI. It's not still saying much about the phenology. So I proceeded in the analysis, and I did phenology analysis because I had the measurements only till February. The only meaningful variables are start of season, that's SOS, max day of occurrence of maximal NDVI or the peak of season, and the value of the peak of season. So if we are speaking about the start of season, we can see that in manipulated plots, the start of season was sooner, but in warming, the standard deviation is really huge. And this is caused by the leading plot, the one which was so much green, and the way how the start of season is in this case specified, because I took as start of the season 20% of the seasonal amplitude of NDVI. And this one plot had the pattern when this 20% of the seasonal amplitude occurred in the day 88, but the average was 120. So that caused really huge variability, and now we cannot really safely say that warming was causing the sooner start of season. We can say it about the warming and reduced precipitation because there is really little standard deviation. If we look at the day when the maximal NDVI occurred, or the peak of season, we can again see that it occurred in manipulated plots sooner than in the control plot. But again, there is a huge variability in the warming. Interestingly, it's not caused by the same plot, but by the different one. Anyways, we cannot say again that that warming was causing the sooner peak of season, but warming and reduced precipitation was causing the sooner peak of season. In case of CI vegetation, it's a very similar story about the start of season. Again, there's the highest variability in the warming, but warming and reduced precipitation is causing sooner start of the season. Day of peak of season was more or less the same. The maximal values are lower in CR vegetation than in CL vegetation because of different plants in there, but there are no differences between the manipulations. Now, we can at this point speculate or hypothesize that this variability is because of different plants, because of different shares of plants in different plots. But in our peatland, we don't have some way how to measure the spectra or the values from just one plant, because there is no patch big enough with only one plant. There is always some mixed vegetation. So that's why I took the peat course with vegetation to Slovakia, to Slovak Plant Care Phenotyping Unit in Nitra, where there is the cultivation facility, which you could see now on pictures. There was the vegetation, but that's the less interesting part. The more interesting part are the cameras in this unit. There is fluorocam for pump-based chlorophyll fluorescence parameters. There is normal RGB camera, and there are two hyperspectral cameras, one with spectral range from 400 to 900 nanometers, another one from 900 to 1700 nanometers. So we did imaging of these 5 peat cores under all of those cameras, and we got the spectra, or we got the images from hyperspectral cameras. And these images are with pretty good resolution, 480 by 600 pixels for the vegetation, which is in pots with diameter 30 centimeters. So I could pick the pixels with just leaves of one plant and then make the average spectra. So what you can see here, it's basically canopy level leaf spectra of different plants. Now I mentioned that there is one till 900, another one from 900 nanometers. For some reason, which I so far don't know why, but there was some change occurring. I will try to solve this. For now, I don't have better solution than just don't look at it. And we have a lot of information in this graph, but there is not much time, and I was speaking so far about NDVI, so I will focus again just on the wavelengths for NDVI. So I was using formula with 670 and 960 nanometers, and we will look at the differences between different plants in NDVI. So here are the values for NDVI, and now what does it say to us? Carex is our grass, which we have there, and there in the peatland vegetation, which I took with myself to Slovakia, there were green leaves and also dry leaves. Now you can see what was the cause of low NDVI for this lagging plot, which was full of litter, because the dry carex has NDVI around 0.4, but the green leaves are around 0.75. So now with this proof, we can quite safely say that these differences are really because of the litter of carex. If you see the graph, there are some non-photosynthetically active vegetation or some parts like dry leaves, flowers, stems, or leaves in senescence. You can see in case of all 4 of them, the NDVI is low. The lowest is for flowers. You can see the spectral pattern in the violet color. These flowers are kind of white pinkish, so you can see that there is also this higher reflectance in red. The stems of Potenella are red, again makes sense. And of course, all of the green leaves are reaching the highest values of NDVI, including the sphagnum, which is our moss. This was very green moss, which I measured in NITRA. The problem in peatlands is that in summer, sphagnum is drying, so the NDVI won't be this high. But we have one more experiment, which may be for other presentation, which is dealing with this problem. At this moment, you can see that if the mosses are green, they have the NDVI as high as the leaves of vascular plants. Last thing before conclusions, which I want to show you are the images, because as I said, this was not just field spectrometer in the unit, but there are really hyperspectral cameras. So you can see the pictures of 4 pots with vegetation under RGB camera, how it looks like in reality. And then we can see on NDVI that even it's possible to recognize the shape of the leaves. But what's interesting is that places where we have the sphagnum, you can really identify that that's very high. You can identify the dry carex, which is very low NDVI, even around 0.25 in the middle of this bright spot. And you can see that there is a bare peat here. There is like no plant. So again, we are in low NDVI, surprisingly not that low. I honestly don't know why, because the other pictures are from the fluorescence camera, and F0 prime is the parameter which is the closest related to sun-induced fluorescence, because it's just the fluorescence of plants which are light adapted, and it's just fluorescence from the first flash of light. And now you can see that the bare peat has very little fluorescence, but the NDVI was still higher. Again, you can see the correlation between NDVI and this fluorescence, because the highest values of NDVI on sphagnum, you can see the spots of the highest fluorescence. Again, here when there are some darker and probably also some peat spots where the NDVI is lower, then there we can see the low fluorescence. So what is important from this presentation, what I wanted to say you, first of all, if we manipulate under future climate, in climate warming, the increased June temperatures can cause the stress to peatland vegetation. For now, I'm saying just probably cause the stress, because I need to do more analysis, but this is the good starting point that we can see. We could identify the warm day when there is really significant difference in between control and warm plots. The vegetation season is starting sooner in warmer and drier conditions. I cannot say that they start sooner in just warmer conditions because of the variability among our repetitions, but the warming and reduced precipitation is causing in both kinds of vegetation which we measure a sooner start of the vegetation. And the variation in the same climatic conditions is caused by the different shares of species in plots, because they are the same species in all of the plots. They are just in different ratios, and the vegetation and its litter really matters for remote sensing. So these are the references which I was using for the introduction, and thank you for your attention.